transcription videos and translation videos for greater insight into these processes. So let's go ahead and begin. We talked about DNA and we went over the process of replicating the DNA, a crude process in order to replicate the DNA called DNA replication. Now we're going to focus on transcription and translation. Transcription focuses on going from DNA to RNA. Translation focuses on interpreting the RNA language into an actual protein sequence, which is responsible for creating the protein structure. So, transcription. Yes, it's a ton more complicated than what you see in the slide, but again, this is just an intro course, so we're just going to highlight some of the more important parts of transcription. So you need to know the steps as outlined in the slide, memorize, as well as know the key enzyme or enzymes. In this case, there is only one enzyme you need to memorize for the transcription process, and that is called RNA polymerase. Now, RNA polymerase is a jack of all trades. In transcription, the RNA polymerase goes ahead and during the unwinding process transcribes a brand new RNA strand. After it transcribes the RNA strand, it then goes ahead and allows the DNA to wind up, at which point the RNA polymerase leaves. So, very straightforward steps. This is as much as you need to know. Assume, at least at this level, that the RNA does everything. So again, really quickly, DNA unwinds, RNA polymerase makes the RNA strand, and then the DNA winds up, and then the RNA polymerase and RNA strand leaves. We're going to assume that it's going to produce a mRNA strand. I do want to point out that there are hidden steps, which I'll talk about later. You do not need to put in these hidden steps when I ask you a transcription summary question. You simply need to put what you see right here. You can use words or you can use a sketch like I've placed here. Here is another sketch. This is taken directly from the book. Here we see again the unwinding process where DNA temporarily unwinds. The beginning part of the DNA strand where it's going to be transcribed, we call this the initiation sequence. The ending is the termination sequence, at which point and I'll just draw it as a block, the RNA polymerase transcribes a brand new strand of RNA, which is what you see right here, and then it winds up. So, very simple on purpose, very straightforward. You are responsible for knowing that. Now, I talked about the hidden steps. It turns out that, going back one slide, the RNA produced isn't directly mRNA. It's a type of RNA called hnRNA. So if you go to slide 4, it's actually hnRNA, which stands for the heterogeneous nuclear RNA. So let me say that again. It actually produces hnRNA, which is heterogeneous nuclear RNA. It turns out that DNA itself actually is a mixture of introns and exons. So exons is actually what we want because it actually codes for known amino acids. Introns, at this point, all we can assume is it's junk DNA, or we just haven't identified the purpose of it yet. So it turns out that, going back a slide, that when we produce a brand new RNA, it's actually going to be heterogeneous nuclear RNA, hnRNA. So what we need to do is what's called a post-transcription. It needs to participate in a post-transcription process, where in this process we have additional enzymes which come in and basically remove the junk RNA that was coded from the junk DNA introns. This then leaves the leftover good exon RNA, which is the mRNA. So these right here are the hidden process steps, the hidden post-transcription process. And I have separate questions on this part. Unless I ask a question on this separately, you're going to automatically assume on slide 3 that it's mRNA. So don't worry about putting in these additional extra steps unless I ask you a separate question on it. Let's go ahead and move on. I've summarized this before, but let me just say it again. 3 nucleotides per amino acid. So in this case, we call these words, so to speak, codons. Codons are degenerate. Keep in mind there are 64 possibilities depending on how you arrange the nucleotides. So there are 64 possible amino acid possibilities. So a lot of them we have duplicate codons for the same amino acid. So we say they're degenerate. A single codon will always code for one amino acid. Just keep in mind that many of the codons will code for the same amino acid, but it still only codes for one at a time. And codons are universal. So we see them in all different levels of organisms, from humans to plants to bacteria. Here are the here are the various amino acids. Here are the codons, which code for the amino acids. Notice we have 1, 2, 3, 4 codons, and here's an example of them being degenerate. They all code for the amino acid alanine. Each codon codes exactly for one amino acid, so AGG codes for arginine, CGA always codes for arginine, and they're universal. Beat that to death. Let's go ahead and move on. Here's a nice summary In addition, they're also precise. Well, I just said that. Chain initiation is AUG. Whenever you see AUG, this automatically tells the translation process that we're going to start here. At some point, as we're coding, as we're making the protein, and we need to know when do we stop making the protein, when is the last amino acid we get to, and when is the protein or polypeptide finally finished, we have to have a ending codon which says, okay, this is when you stop. So we call this the chain termination. And keep in mind, the code is almost universal pretty much for all organisms. As far as this class goes, it is universal. And let's move on. Translation process. This is a good place to stop.